We are back to our last problem, so let's go ahead and take a peek at a phase diagram. So I have an alpha phase right here, there's a beta phase right here, so this is beta plus liquid. This is going to be an alpha plus a beta phase right here. This is going to be this beta plus HFV2. This is going to be HFV2 plus liquid. This is going to be liquid plus V. This is going to be this plus this delta phase. This is going to be this plus this delta phase. So, and then this little guy right here is going to be this phase plus liquid. So, I filled out all the sage. Also based on the maximum solubilities, draw the concentration profile of the fusion couple at some intermediate time not equal to 0. Ooh, excellent. So, looking at the values here, in my pure alpha phase right here, I see that for pure hafnium, for the alpha phase, I really can't put too much vanadium into my hafnium. But meanwhile, I can put quite a bit of hafnium into my vanadium and still be in that vanadium phase. So I know that the diffusivity of hafnium is going to be much greater than my diffusivity of vanadium. So if I were to draw a diffusion couple of HF, vanadium, and if I were to draw, it would look like this. So hafnium goes in here, vanadium goes into right there. So that would be where I can draw those lines. Excellent. So, fantastic. Now, let's remember our eutectic. So, eutectic, let's have void, we have peri, dick, and then peritectoid. So remember here we're going from liquid to alpha plus beta. Eutectoid, we're going from basically a gamma to an alpha plus beta. For peritectic, liquid plus alpha to a beta. For peritectoid, we're going from a gamma plus alpha to a beta. So there we go. So let's go ahead and let's see where we find these. So I can see here, this looks like a eutectic. So we're going from a single phase region, beta, down here to, what is this phase right here? Actually, we forgot to write this one. This one plus this. So I'm going from a solid phase to another solid phase, so that's a eutectoid. So single solid phase to a two-phase solid region. Here, I'm going from liquid to two-phase solid region here, so that is a eutectoid. Excuse me, eutectic. So this is a eutectic going from liquid to alpha plus beta. If we look over here, we also have congruent melting points here. We have another congruent melting point right here. We also have another congruent melting point right here. This liquid to a two-phase region, so that's another eutectic. And then finally, I have a liquid plus a solid phase to a new solid phase. That is going to be a peritectic. So liquid plus solid to a new solid phase. So there we go. Those are our points for our congruent melting points. We have invariant points, and we've named them as well. Which has a higher diffusivity? We've already answered that question from the answer above. All right, so let's look at a composition of 50 weight percent at 1600 C. What phase exist in this region? How can I relate to the chemical potentials? What is the composition of each phase? What's the fraction? So let's answer all those questions. So I'm at 50%, and I'm at 1600. So I'm like right here. So I'm in a two-phase region. So I know my chemical potential of my liquid is equal to my chemical potential of the vanadium. So I've got that right off the bat. What else does the question ask? So I've got, how can I relate the chemical potentials? So we know that we've answered this question. What phases exist? Again, liquid plus vanadium. And then now, what's the composition of each phase? And then what is the fraction of the material? So composition, again, is pretty straightforward, right? So I have my liquidus line, and this is my solidus. So my concentration in the liquid phase is going to be equal to what? It looks like 45% vanadium. My composition of vanadium in that phase, the V phase, I can see that's approximately 90. So that's my compositions. Now the fractions are given by my lever rule. So that's, again, my fraction in the lever rule. Again, I always divide out by the full spectrum, so it's going to be minus 45. So my initial composition, so if I'm looking for the fraction of the liquid phase, you see here, I'm closer to the liquid, right? I just have to travel this distance for that liquid. So if I want for the fraction, I'm doing the opposite side. So I don't go to the liquidus, I go away from the liquidus. So it's actually going to be 90 minus my composition, which is 50. So there we go. And then finally, for the vanadium, it would just be the opposite. So again, still the full length, 90 minus 45, but then it would be 50 minus 45. There we go. That's it. So got my compositions, answered all that questions. Draw the free energy curves. Ooh, I like that question. So if I were to draw the free energy curves here, so let's go ahead and draw. So I've got my G, I've got my compositions here. So I've got basically a point at 45, and then we have another point at 90. Because if we look at 1600, ooh, actually I've got many more phases. Ugh. All right. So actually, let's see if I could draw this intelligently. Actually, let me zoom out here. So I'm going to zoom out. So let's take a viewpoint. Let's zoom out. So I'm at 1600. So I'm going to draw the exact same distance here. So my first phase that I'm in is my alpha phase. So I'm going to make my alpha line this blue line. So I'm right here, and then it's instantly like that's the only time I'm in that phase. And then I cross over into this two-phase region of alpha plus beta. So in between here and this, so I'm going to draw lines. So I'm going to draw the lines like this. Let's draw this line. Let's draw when we cross over to this line. Let's draw when we cross over into here, 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 and then we're safe until here, and then we're safe until here. So in between this region here, so in between this line here, and then even closer. Sorry, there's one more here. So there's like an infinitesimal time when I'm here. But anyways, I'm in this two-phase region right here. So here I'm in my two-phase region. So that means in my beta, so I'm in pure beta from here to here. So let's kind of draw this. Oh, it's getting messy. So that's my pure beta. So in this region here, I'm alpha plus beta. So I'm going to have a point here. So here I have a common tangent. So I'm in a two-phase region here, and then I'm a common tangent, and then I have my single-phase region right here. And then I cross over into, again, a two-phase region of liquid. So my liquid is going to be this different color gray. So again, I'm going to have a common tangent between here and here. So again, any region where I'm in a two-phase region, I have a common tangent. So you can see here that this is the lowest energy phase, so I'm in a pure beta. So actually, we could draw this out a little bit further here. So, for example, right here I'm in alpha. Then I'm in alpha plus beta. Then I'm in beta. Then I'm in beta plus liquid. And then from here to here, I'm in pure liquid. And then I'm in liquid plus vanadium, then vanadium. So my curve continues. I'm still low. And then, sorry, let me undo that. So my curve continues. I'm still low. And then I'll kind of jump up here. So that's going to jump up. And now my vanadium curve, which is going to be my red curve here. So my vanadium curve starts something over here. And then it's going to end up like this. So I have, again, a common tangent between, basically this point and this point. So actually, excuse me, between these 2 points here. So the common tangent exists throughout these 2 points. So common tangent here. So for this two-phase region, common tangent here. So actually, let me redraw my line like this. Let me redraw this one too. So I'm going to continue drawing here. And then let me draw my red line. So again, I could draw my common tangent between here and here. So a common tangent line. And then my vanadium is my last phase. So the key idea is, again, I have a common tangent between the slopes whenever I'm in these two-phase regions. So common tangent, common tangent, common tangent, common tangent. That's it. Single phase region, you see which curve is the lowest, and then that's all there is to it. So that would be my free energy curve. And again, we have a couple other videos that kind of show you how to do this a little bit cleaner. But anyways, that was difficult. All right. I know I have a common tangent when two phases are in equilibrium, but how can you relate the common tangent mathematically to the thermodynamic variable that tells us when two phases are... Ooh, excellent. So I know that my chemical potential, mu is equal to dG dN by constant temperature and pressure. So dG dN, again, N is like your number of moles or number of atoms, but I can also write this as, with some, there's going to be a prefactor out here, but you could rewrite this as the mole fraction. So this is the slope of your line. So again, when I have a common tangent, my slopes at 2 points are equal, and thus the chemical potentials are equal. So that's all we were getting at with that question. So that's it. So good luck on your exam, and I'll see you on the exam day. Good luck. Thanks. Bye.